All right, welcome to Differential Equations, Math 330, Chapter 2, Section 4. We are going to explore numerical methods for solving first-order differential equations using Euler's method, or Euler's method, depending on how you pronounce it. All right, so what we've always had is this differential equation, some differential equation where we have an independent variable like x and a dependent variable like y. So what does this differential, first order differential equation tell us? Well, it gives us the slope of the solution curve. So we're going to use this idea. So let's say I had some point x1, y1 in my range here. And so then, knowing this differential equation, I could calculate the slope of my solution curve at this point. So there's my slope, right? So now from that, I'm going to go some step size h into the future, let's say, of the x coordinate. So if I do that, I can predict where my y point should be as long as I assume my slope is constant along this interval of h. So to do that, I would get to, and then I could find my y-axis. I would get two new points. So to do that, I apply my definition of a slope that's rise over run. And then my difference between the two x points is just my step size h. And then I can solve for my new y coordinate. So this is Euler's method. So if you assume we know a previous point we call n, and I can calculate the slope at n at this point, then I can calculate the future location of my y at n, or my n plus 1 y. So if we do this, we can try to predict. Now there's error involved in here. Our step size has to be chosen carefully. If we choose it too big so that the slope of our solution curve changes too drastically, this will not value. So what we're going to do is start off at problem 1, where they give us this differential equation, and they give us its initial condition, and they give us the exact solution. So they want us to find the solution of this at y equals a half, and they want us to use step sizes of 0.25. So to do this, so I'm going to apply Euler's equation to predict this. So in Excel or in a computer program, you can set up this grid. So I have a grid of n, n, xn, yn, the value of my slope with the values of xn and yn, the exact solution, and the error. Well, what is error? Error is the difference between the exact solution and my predicted y solution. So starting out at my initial condition, x equals 0, y equals 2, my exact solution matches my solution for y. So I have 0 error. So now what I'm going to do is add h, which is 0.25, to x, and I get my new x position. So how do I get my new y position? Well, to do that, I apply this Euler's method up here. So my past y is 2 plus my h, which is 0.25 times my slope. Well, my slope at my past location here is a minus 2. So I have minus 2 times 0.25 plus my y value of 2, and I get my new y value of 1.5. Now, that does not match my exact solution, but it's close enough. It's only off by a half of a second decimal place, so it's not bad. And then if I do another state batch, I go to another step size h, I get to the x value I want to know, and then I do my calculation again. Here's my y of n. I calculate what my function should be at those locations, which is this, a minus 1.5, because my slope is just minus y. And then I multiply that times h and add it to here, and I get this value. And so I can do this one, I can just keep going. But now my error has increased. Now it's a little bit larger, and that's the problem with Euler's method. If your slope changes drastically, you have to decrease the amount of size h. Well, this is just to give you a test, or a flavor of what Euler's method should be. We're going to do 2 or 3 of these in class today, so you need to bring your computer. So I'm just going to remind you to bring your computer to the next class period. Thank you.